Exploratory data analysis refers to a set of procedures for producing descriptive and graphical summaries of data. A benefit of exploratory data analysis is that it allows you to examine the data as they are without making any assumptions. It is a useful way to examine your data, understand relationships among variables, and identify any problems such as data entry errors. There are 5 learning objectives for this session. Once you achieve these objectives, you will be ready to work with a data file and begin to explore the information it contains. All of the examples in this session use data from the Program for International Student Assessment, or PISA. According to the documentation, PISA is an international assessment that measures students' ability to use their knowledge and skills to meet real-life challenges. It began in 2000 and it takes place every 3 years. In each administration, 15-year-old students are testing in reading, mathematics, and science. There are also background questions that ask about an examinee's home, family, and school characteristics. Examples in this session use data from the 2012 PISA mathematics exam and background questions. Data involved 24,144 examinees from 64 different countries. Identifying the type of data contained in a variable is a critical first step in data analysis. It allows you to identify appropriate statistical procedures. There are 4 types of data: nominal, ordinal, interval, and ratio. Nominal and ordinal data are also referred to as categorical data. Interval and ratio data are also called continuous data. When identifying the type of data for a variable, it is helpful to first decide whether the data are categorical or continuous, and then identify whether the data are nominal, ordinal, interval, or ratio. With nominal data, values represent discrete units that have no inherent ordering. Examples include gender and eye color. To see that order does not matter with nominal data, change the order of the values. The meaning does not change. For example, listing male and female is no different than listing female and male. Ordinal values also represent discrete units, but values are inherently ordered. An example is the finish order of runners in a race: first place, second place, and so on. The main limitation is that the distance between units is not the same. As you can see on the slide, the difference between a 1 and a 2 is not the same as the difference between a 2 and a 3. In terms of the running example, the difference between first place and second place could be an inch or it could be 10 feet. Likewise, the distance between second and third place could be 3 feet or 20 feet. Interval scales build upon ordinal scales by having ordered units of the same size. That is, the distance between units is the same. The difference between 5 and 10 is the same as the difference between 20 and 25. Interval scales are commonly encountered in social science research. For example, test scales are commonly designed to represent an interval scale. Like any other interval scale, they are limited by not having an absolute zero. For example, a live person cannot have 0 intelligence. Moreover, the origin of an intelligence scale could be 10 or it could be 1,000. The choice is arbitrary because interval scales have no absolute zero. As a consequence, you cannot make statements such as a person with an IQ score of 160 is twice as smart as someone with an IQ score of 80. Ratio scales are common in the physical sciences, but hardly ever used in the social sciences. Ratio scales have all the properties of an interval scale with the additional property of having an absolute zero. An example is length. Measurement of length begins at 0. Now let's look at some examples of the different data types in the PISA data. Which 2 variables in the table are nominal? Yes, country and gender are nominal variables. The ordering of these variables does not matter. Now, which variables are ordinal? Grade is ordinal, but what about books? This variable represents the number of books in the home. Is the number of books ordinal, interval, or ratio? The answer is not as easy as it seems. Let's look at the specific text of the question. If the data were recorded as the actual frequency count of the number of books in the home, it would be a ratio scale. There are equal units and an absolute zero. However, as you can see by the text of the survey question, the frequency counts were grouped into ordered intervals. Moreover, the number of units in each possible response option is not the same. Therefore, this variable is actually ordinal. It is always important to know what your data actually represent in order to determine the data type. Look at the last variable. What type of data is it? Yes, the last variable is an interval scale. Mass scores do not have an absolute zero, but units are the same. Test scores are commonly assumed to be interval, and PISA involves a scaling methodology that helps guarantee that the scale is actually an interval scale. So why does it matter? Why do we need to know the type of data contained in a variable? The answer is, it matters a lot. Statistical methods are designed to work with certain types of data and not others. Many of the methods you use to analyze continuous data are not the same as methods you use to analyze categorical data. If you do not know the type of data, you can produce the wrong analysis. On a more positive side, there are many statistical methods available for data analysis. Knowing the type of data limits the realm of possibilities and helps you more easily choose the correct method of analysis. Let's look at some basic descriptive statistics. When we collect data on a single variable, they are not all the same value. Rather, we have a distribution of values. Central tendency refers to the location of this distribution. It represents the typical value, or the value we would expect to get from a participant. We have three choices for describing central tendency: the mean, median, or mode. The mean is the arithmetic mean, and the equation for it is shown here on the slide. The median is the 50th percentile, which is denoted as P50, and that is also known as the second quartile, denoted as Q2. It's the point where 50% of the observations fall below that value. The mode is the most frequent value, and there can be one or more modes in the data. Although central tendency tells us about the center of the distribution, it does not accurately represent every value in the distribution. Participants can have values quite a bit lower than the mean or substantially greater than it. As such, we would also like to know about the distribution's variability. The dispersion or spread of values in a distribution is quantified through the range, standard deviation, or interquartile range. The range is simply the maximum value minus the minimum value. And the standard deviation can be computed with the equation you see on the slide. The interquartile range is the difference between the third quartile and the first quartile. You now see that you have various choices for describing central tendency and variability. Which one do you use? It depends on the type of data. You can see that with nominal data, you can summarize the information through frequencies, proportions, also known as relative frequency, or percentages. You can illustrate the information with a bar chart or a pie chart. Ordinal data is summarized in a similar way, but you have the additional choice of using percentiles. You can also use the mode or median to describe central tendency, and the interquartile range to express variability. With ordinal data, you can also use a bar chart or pie chart to illustrate the results. You really have the most choices with continuous data. You can summarize the information through percentiles, you can look at the mean, median, or mode for central tendency, and you have a choice among the standard deviation range or interquartile range for variability. The plots are different than you had with categorical data. For continuous data, you illustrate the information through a histogram or a box plot. Now let's return to the PISA data and look at some examples. This slide shows a summary for the country variable. Data are summarized in tabular form as frequencies and percentages and illustrated as a bar chart. You can see that Most examinees came from Japan, while the fewest number of examinees came from the United States. The bar chart is a graphical representation of the information in the table. A key feature of the bar chart is that the bars do not touch each other. This characteristic indicates that the values are categorical and not continuous. It is an appropriate way to plot categorical data. The summary for the number of books in the home appears to be very similar to the last slide. There is a tabular and graphical summary. However, the values shown on this slide are ordered. This means we cannot swap the rows in the table or change the position of the bars in the plot without altering the meaning of the values. We must present them in order, 0 to 10, 11 to 25, and so on. Or we can present them in reverse order, 500 plus, 201 to 500, and so on. No other ordering would be acceptable because the values are inherently ordered. We cannot arbitrarily choose the order. Here we see a way to summarize continuous data. The table lists the minimum and maximum values along with the mean and standard deviation. We learn even more about the distribution through the histogram. Mathematics scores have a unimodal and symmetric distribution. A histogram is a good way to illustrate central tendency, variability, and the shape of a distribution. It is also a good way to identify multiple modes if they exist. However, a histogram is not a good way to identify outliers. A box plot is an alternative and more robust way to illustrate a continuous variable. The horizontal lines in the box plot have specific meaning. The center of the distribution is noted by a thick line at the 50th percentile. Variability is represented by a box that is formed by marking the first and third quartile. This box depicts the interquartile range. Whiskers extend from the box to the lower and upper fence. When there are no outliers, the lower and upper fence are the minimum and maximum values respectively. When outliers are present, as in this figure, the lower and upper fence have a different meaning that will be described later. Outliers and extreme values are noted with special marks, such as small circles or stars. A box plot is a useful way to illustrate central tendency, variability, and skewness of a distribution. It is also an excellent way to identify outliers and extreme values. You will not be able to identify the number of modes in a distribution with a box plot. A histogram is much better for identifying the number of modes. Histograms and box plots have benefits and limitations. For this reason, you should create both when exploring your data, but only choose one for a report. Choose the plot that tells the best story. If you have a unimodal distribution with outliers, use a box plot. If you have a bimodal distribution, use a histogram. In exploratory data analysis, we often want to learn about the relationship between two variables. We may be interested in questions such as, how do values of one variable change as values on another variable change? Do low scores on one variable correspond to low values on another variable? Do large values of one variable correspond to large values on another variable? Describing the relationship between two variables is more complicated than methods we have already discussed because you must consider the type of data in both variables. Data for both variables might be continuous or they may be categorical, or one may be categorical and the other continuous. These combinations lead to different statistical and graphical summaries. Note that a necessary condition for describing the relationship between two variables is that each participant has values on both variables. If a participant is missing values on one or both variables, they cannot be included in the analysis. Let's look at a summary for two categorical variables. The slide shows the relationship between the number of computers in the home and an examinee's home country. You can see that country of origin is related to the number of computers in the home. Most Costa Ricans have no computer in the home, whereas a majority of Norwegians have 3 or more. It is likely that the number of computers is a proxy for the economic conditions for a country, and that is the reason for the relationship. Data for these two variables are presented in tabular form as a contingency table. Values for one variable make up the rows of the table, and values for the other variable comprise the columns. Cells in the table list the percentage of total observations. You could also include row percentages and/or column percentages if you wanted to also present the percentage for each variable alone. Although it is beyond the scope of this session, the relationship between two categorical variables can be reduced to a single statistic, such as the phi coefficient, or Kramer's v, and tested for statistical significance with a chi-square test. However, for the purpose of exploratory data analysis, a contingency table is fine. The figure in this slide shows a conditional bar chart, a graph that shows a bar chart for one variable at each value of the other variable. You may be more familiar with describing the relationship between two continuous variables. For this summary, we can present descriptive statistics for each variable or describe the relationship between them with a correlation. A scatter plot is the appropriate way to illustrate the relationship between two continuous variables. We will learn more about correlation later in the semester. Less obvious is the way to illustrate the relationship between one continuous and one categorical variable. A side-by-side box plot shows a box plot of the continuous variable at each value of the categorical variable. This figure shows the distribution of mathematics scores at each value of number of computers in the home. You can clearly see that as the number of computers increases, so too do mathematics scores. The relationship is also evident in the table, where mean math scores are presented for each value of the number of computers. At this point, you have seen a variety of ways to summarize data with descriptive statistics. Even when you reduce the number of choices by identifying the type of data, you may still have to choose among a variety of procedures. You may be wondering, how do I know when to use the median instead of the mean? Or when should I use the interquartile range instead of the standard deviation? Or when should I use a box plot instead of a bar chart? The answer depends on what you learn while you're exploring the data. Outliers and extreme values are unusually large or unusually small values. They are easy to spot with a box plot because they are values that extend beyond the fences. Outliers extend beyond the inner fence. The lower inner fence is defined as the first quartile minus 1.5 times the interquartile range, and the upper inner fence is the third quartile plus 1.5 times the interquartile range. Extreme values extend beyond the outer fences. The lower outer fence is defined as the first quartile minus 3 times the interquartile range, and the upper outer fence is the third quartile plus 3 times the interquartile range. If you see an outlier or extreme value, the first thing you should ask yourself is, did I make a data entry error? The outlier could simply represent human error when the data file was created. Check the value and correct it if that indeed was the problem. If the value is a legitimate outlier or extreme value, you should consider the use of robust statistics such as the median and interquartile range because of the way outliers can influence the mean and standard deviation. To see the influence of outliers on the mean and standard deviation, let's use the data shown on this slide. You can see that the mean and median are similar when there are no outliers. The same holds for the standard deviation and interquartile range. Now let's change just a single value in the data and make it an outlier. We will change the 9 to a 20. Notice how much the mean and standard deviation changed, while the median and interquartile range did not change at all. The median and interquartile range are robust statistics. They are suitable ways to describe central tendency and variability in the presence of outliers and extreme values. Thus, if you have outliers in the data that have a strong influence on the mean and standard deviation, you should use the median and interquartile range to describe central tendency and variability. When evaluating the relationship between two continuous variables, you can have an outlier on both variables. This type of outlier is easy to identify in a scatter plot. You can see in the example on the slide that the solid filled circle is a bivariate outlier. It has unusual values on both variables. We will return to this idea when we discuss correlations, but for now know that a bivariate outlier can have an adverse impact on the Pearson correlation coefficient. If you notice a bivariate outlier, you may want to use a Spearman rank order correlation instead of a Pearson correlation. More on this concept later in the semester. John Tukey was a mathematician from Princeton who had a profound influence on mathematics and statistics. He is credited with the development of exploratory data analysis, and he invented several of the plots that you know, such as the box plot and stem and leaf plot. He also impacted other fields. For example, he coined the term software, a term we use daily to refer to a computer program. Tukey felt that graphical displays were central to data analysis. He wrote that the best single device for suggesting and at times answering questions beyond those originally posed is the graphical display. I agree with this sentiment, and this is why you should begin an analysis with exploratory methods. I often tell students that there is an art to statistics because statistical summaries must be interpreted. Tukey expressed this idea in a quote: "Doing statistics is like doing crosswords, except that one cannot know for sure whether one has found the solution." This aspect of statistics can be difficult for students who want an exact answer. With practice, you will become more comfortable exploring and interpreting your data.